Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Solitons in Two Dimensions from the paper Classical Mechanics. So students, let us see what we are going to learn in this module. In this module, we will learn the distinction between solitary waves and solitonic solutions. Also, we will learn to obtain the static solutions of a relativistic classical theory in 1 plus 1 dimensions, which is specified by certain nonlinear potential energy functionals. Furthermore, we will learn about the boundary conditions which are satisfied by the localized solutions as x goes from minus infinity to plus infinity. Now, many dynamical systems in physics admit wave equations that in general contain nonlinear and dispersive terms. The wave equations may have coupled fields in one or more spatial dimensions. The dynamical system may or may not be relative invariant. We will be concerned here with the relativistic Lorentz invariant systems in one space and one time dimensions that exhibit solitary wave and solitonic solutions. Now, finding one localized solution of a given nonlinear wave equation is in general enough to establish the existence of solitary wave solutions. On the other hand, for soliton solutions, we need many time-dependent solutions which are consisting of arbitrary number of solitons. It makes the task of finding soliton solutions quite daunting. If we have a nonlinear equation, it is not easy to know whether the equation allows soliton solutions. Obtaining the solution allows is even more difficult. In this unit, we will describe two examples of a scalar field phi of xt in 1 plus 1 dimensions. As a first example, we will consider a Cp raised to power 4x theory, and Sine-Gordon equation will be our second example. Delta S is equal to delta integral over dt integral over dx Lagrangian L, which is a function of x and t and is equal to 0. This gives rise to the equation of motion, that is del square phi of xt by del t square minus del square phi of xt by del x square is equal to minus del u phi of xt divided by del phi of xt. This is the wave equation satisfied by the scalar field phi of xt. The nonlinear terms depend on the potential function u of phi. Let the absolute minima of u of phi occur at phi is equal to phi 1, phi 2, etc., where its value is 0. That is, u of phi is equal to 0 or del u phi by del phi is equal to 0 for phi is equal to phi 1, phi 2, and etc. The Hamiltonian or the total energy functional can be easily obtained from the Lagrangian density and is given by E phi is equal to the integral going from minus infinity to infinity dx into within the curly brackets 1 by 2 del phi by del t whole square plus 1 by 2 del phi by del x whole square plus u of phi. For constant field in space-time, E of phi is equal to 0 for phi is equal to phi 1, phi n, etc. 1 by 2 del phi by del x whole square is equal to u of phi. Since both del phi by del x and u of phi vanish at x is equal to infinity, therefore the integral constant is 0. We next move on to study the phi raised to power 4 theory. As an illustration, we consider a phi raised to power 4 theory to obtain what is known as the king's solution. Such a theory was considered by Dashin, Goldstein and Jacques and by Polyakov. The potential energy function considered by them is u of phi is equal to 1 by 4 lambda into the square of phi square minus m square by lambda. Here, m square and lambda are positive constants. The potential has two degenerate values given by phi is equal to plus minus m by square root of lambda. That is, u of phi is equal to 0 for phi is equal to plus minus m divided by square root of lambda. The potential also has a maxima at phi is equal to 0. The localized solutions we are looking for must tend to plus minus m by square root of lambda as x tends to plus minus infinity. The static solutions can thus be of two types. First, phi is equal to minus m by square root of lambda at x is equal to minus infinity and end up with phi is equal to m by square root of lambda at x is equal to plus infinity. Second, phi starts as phi is equal to m by square root of lambda at x is equal to minus infinity and ends up with phi is equal to minus m by square root of lambda at x is equal to plus infinity. The static equation del phi by del x is equal to plus minus square root of 2 times u of phi can be solved to give x minus x naught is equal to plus minus the integral going from phi of x naught to phi x d phi of x divided by square root of lambda by 2 into phi square minus m square by lambda whole square. Choosing x naught such that phi of x naught is equal to 0, the integral can be evaluated in terms of tan hyperbolic function by substituting phi is equal to square root of m square by lambda tan hyperbolic eta to obtain phi of x is equal to plus minus m by square root of lambda tan hyperbolic m by root 2 into x minus x naught. The solution with positive sign is called the kink and the one with negative sign anti-kink. So, phi kink of x is equal to minus of phi anti-kink of x, which is equal to phi anti-kink of minus x. The energy density of the kink solution is E of x is equal to 1 by 2 d phi by dx whole square plus u of phi, which is equal to 2 times u of phi. So, E of x is equal to 1 by 2 times lambda into square of phi square minus m square by lambda, which equals m raised to power 4 by 2 lambda into secant hyperbolic raised to power 4 of m into x minus x naught divided by square root of 2. This can be easily integrated to give the total kink energy called the classical mass MCL. So MCL is equal to the integral going from minus infinity to infinity E of x dx, which equals 2 times square root of 2 divided by 3 into m cube by lambda. Let us discuss the solitons in 2 dimensions. Consider a single scalar field that is phi of xt in 1 plus 1 dimensions whose dynamical evolution is given by the Lorentz invariant Lagrangian density. That is, L of xt equals 1 by 2 into del phi xt by del t whole square minus 1 by 2 del phi xt by del x whole square minus u of phi of xt. The potential U of a function of phi of xt is a positive semi-definite function of phi of xt. The Lagrange's equation of motion is obtained by extremizing the action. That is, delta S equals the delta of integral of dt into the integral of dx into Lagrangian of xt equals 0. Now, given the static solution, which is described in equation 30.14, we can obtain the moving solution by Lorentz transformation of the space coordinate x to obtain phi u of xt equals tan hyperbolic of m divided by root 2 into x minus ut minus x naught divided by square root of 1 minus u square. Here the velocity u lies between minus 1 to 1 in units of velocity of light. We should mention that the solutions which are discussed above are solitary wave solutions. They are not the solitonic solutions in the sense that they do not retain their shape after collisions. The proof is beyond the scope of the present. The figure shows that phi of x has a kink at x is equal to x naught. That is, for the solutions with positive sign, phi of x has a kink. And in the second part, where phi of x has an anti-kink at x is equal to minus x naught. The energy density of the kink is also plotted as a function of x and is found to have a peak at x is equal to x naught. Let us now move on to Sine-Gordon system. The static solutions discussed above are solitary waves and are not solitons. We consider now a single scalar field phi of xt in 1 plus lambda dimension with a Lagrangian density that admits solitons and solutions. Lagrangian of xt is equal to 1 by 2 into del phi by del t whole square minus 1 by 2 into del phi by del x whole square plus m raised to power 4 by lambda into within the brackets cos of square root of lambda by m into phi minus 1 brackets close raised to power 7. The field equation arising from the above Lagrangian density is given by del 2 phi by del t square minus del 2 phi by del x square plus m cube by lambda into sine of square root of lambda by m into phi is the well-known Sine-Gordon equation. In order to solve this equation, let us first make a convenient transformation of the field phi and the variables x and t for the sake of simplicity. So x prime is equal to mx and t prime is equal to mt and phi prime is equal to square root of lambda divided by m into phi. In terms of the transformed quantities, the Lagrangian becomes Lagrangian of x prime t prime is equal to m raised to power 4 by lambda into within the brackets 1 by 2 of del phi prime by del t prime whole square minus 1 by 2 into del phi prime by del x prime whole square plus cos phi prime minus 1. The equation of motion is del 2 phi prime by del t prime square minus del 2 phi prime by del x prime square plus sine of phi prime of x prime t prime is equal to 0. The total energy density Hamiltonian is given by E of x is equal to m raised to power 4 divided by lambda into within the brackets 1 by 2 into del phi prime by del t prime whole square plus 1 by 2 into del phi prime by del x prime whole square plus 1 minus cos phi prime. The Lagrangian and the equation of motion are invariant under the following discrete symmetry. First, phi prime of x prime t prime tends to minus phi prime of x prime t prime. Second, phi prime of x prime t prime goes to phi prime of x prime t prime plus minus 2n pi, where n is an integer. The potential u of phi prime is equal to 1 minus cos phi prime, which vanishes at the absolute minima given by phi prime of x prime t prime is equal to 2n pi. All finite energy configurations, irrespective of whether they are static or time dependent, can be divided into an infinite numbers of sectors, which are topological and characterized by a conserved pair of integers n1, n2 corresponding to the asymptotic value 2n1 pi and 2n2 pi that the scalar field phi prime x prime must approach as x prime tends to minus infinity and plus infinity respectively. The static solutions connect the neighboring minima of u phi prime, that is n1 minus n2 equals plus minus 1. The total energy of the soliton can be evaluated using the solution which is described in equation 30.28 in the energy density expression and integrating over x. Then we get m of sol equals 8m cube divided by lambda. The moving soliton solution is obtained as before by Lorentz transformation of x prime minus x naught prime by x prime minus x naught prime tends to x prime minus ut minus x naught prime divided by square root of 1 minus u square. The Sine-Gordon system also permits a soliton-anti-soliton and soliton-soliton doublet solution. A detailed discussion and description of the solution to really conform to the requirement of solitonic solution, which demands shape preservation after collision has been established. It is beyond the scope of the present study. The explicit static solutions are obtained as in the case of phi raised to power 4 theory, namely x prime minus x naught prime is equal to plus minus integral going from phi prime of x naught prime to phi prime of x prime d phi by square root of 2 u of phi prime, which is equal to plus minus the integral going from phi prime of x naught prime to phi prime of x prime d phi by 2 sine phi by 2. This can be easily integrated to give log of tan phi prime of x prime divided by 4 is equal to x prime minus x naught prime, and we get phi prime of x prime is equal to phi sol of x prime minus x naught prime, which is also equal to 4 times tan inverse exponential of x prime minus x naught prime, or phi prime of x prime is equal to phi of anti-sol x prime minus x naught prime, which is equal to minus 4 tan inverse exponential of x prime minus x naught prime. This is also equal to minus phi sol of x prime minus x naught prime. The soliton solution goes from phi prime equals 0 to 2 pi, or from 2 pi to 4 pi, etc., as x goes from minus infinity to plus infinity. The anti-soliton solution goes from 0 to minus 2 pi, or from minus 2 pi to minus 4 pi, etc., as x goes from minus infinity to infinity. The figure shows the Sine-Gordon soliton phi prime x prime varying with x. So students, let us now summarize what we have learned in this module. Relativistic classical phi raised to power 4 field theory in 1 plus 1 dimension with the potential energy function u phi equals 1 by 4 lambda into square of phi square minus n square by lambda as localized solitary wave solution called kink and anti-kink with the total kink energy MCL equals 2 root 2 by 3 into m cubed by lambda. Relativistic classical Sine-Gordon theory in 1 plus 1 dimension has discrete symmetry and has localized soliton, anti-soliton and multiple soliton anti-soliton solutions. The static solutions connect the neighboring minima which are separated by 2 pi, and that phi goes from 2n pi to 2n plus 1 pi as x goes from minus infinity to plus infinity. Thank you students for your attention.